Okay, any questions? Hannah? Oh, you noticed. Yeah, this is not Thurston 203 anymore, right? Now, what happened there? Well, I got locked out of the building. They won't let me go in there and use that nice pre-installed recording device for the blackboard and all that kind of thing anymore, not for now at least, so I have to improvise. So here we are. We're actually in my house right now, and yeah, so that's how we're going to do this. I'll explain how it works in a minute. Any other questions? Bryce? Yeah, that's a Hamilton poster back there. That's for, we went to see Hamilton in a couple summers ago, and my sister got a couple of us framed posters of the show, which is pretty cool. I mean, it's such an awesome thing. If you haven't seen it, I'd strongly suggest you do it. It's really amazing. But anyway, yeah. So, any other questions? Back row, Alex. Yeah, you don't have a question. Okay. Anybody else? Robert. Yeah, I know. Robert and I agree that this class works best with a blackboard. So how are we going to do this without a blackboard? You may say. Well, you may ask. Not going to do slides, because if I try to teach a course with slides, then I'm going to go way too fast. So here's what I'm going to do, and this is what I've been doing for my other class for most of this time. I'm going to give the lecture to you, to the computer, and I'm going to try to imagine you're here in my house with me, hanging out, and while I'm talking to you, I will write on these pieces of paper what I would be writing if I were writing on the board. Okay, that enables me to control the speed of presentation so that it matches as closely as possible what's going on in an actual classroom. And when I'm done making this recording, I will scamper over to Rhodes Hall and scan these pages, and when I upload the recording to Canvas, I will upload a PDF of that scan so you can follow along as if you're watching the board being created. Although it won't be as suspenseful as watching the board being created, because you'll have the whole thing to look at to begin with. So anyway, that's how this is going to work. And fortunately, you only have to endure this for 2 lectures, because this is the second to last lecture. And so any questions about that? Any questions about how we're going to do this? Sam? I'll try. Okay, that's the best I can do. Okay, so where were we last time? We were talking about the general space of stuff we were talking about was this whole idea of IIR systems governed by difference equations, causal IIR systems governed by difference equations, and at the very end of class time, we had started talking about the Z transform. And this is a key math tool for analyzing linear time-invariant systems, especially causal linear time-invariant systems governed by difference equations. And we'll get back to those after I finish talking about the Z transform itself. Okay. First off, the first thing we did, and this is something we had to do when we introduced the IIR systems governed by difference equations, we're restricting our attention for the most part for now. So for now, we're restricting our attention to what I've been calling the universe of signals that are 0 for negative time. So 0 for n less than 0. So those are the kinds of signals we're talking about. And I want to emphasize for now because later on we're gonna back off of that assumption. Okay. For a general signal, not just ones in the universe, the Z transform of a signal x of n, if it exists, is given by sort of 2 parts. One part is the formula, x of z equals the sum from n equals minus infinity to infinity, x of n, z to the minus n. And because we're restricting our attention to signals in our universe, so this is because universe, this is actually only a sum from n equals 0 to infinity of x of n z to the minus n, because x of n is 0 for n less than 0. That's the formula for x of z. And here z is a complex variable. And then we have this region of convergence, okay, the ROC. And this is something that in this course we don't have to worry about so much. It's always of the form something like this, r sub a less than magnitude of z less than infinity. Okay, so don't worry too much about this. The point is here, z is a complex variable. This power series may or may not converge, depending on what the value of z is. Maybe it'll converge for no values of z. In that case, the signal doesn't have a z transform. But if it does converge for some values of z, it always converges for all z's bigger than equal to some smallest radius r sub a. That just turns out to be the case, and we'll see that come up in all the examples we look at. Okay? So we started talking about some examples. So started with examples. And what do we see? First off, we saw the impulse. That's always the first signal we want to start with. And the notation we use for a signal in a z transform is a double arrow with a z over it. So x of z equals 1. And this converges for all z. So we write 0 less than magnitude of z less than infinity. In fact, it converges for z equals 0, but who cares? You know, we don't include the 0 in the region of convergence. And we also saw u of n, x of n equals u of n. We figured out what that z transform was. That was x of z is equal to, and here's where another place where I differ a little bit from the book. I like to write my z transforms as functions of z rather than z inverse. Now, what is the ROC for this one? It's 1 less than magnitude of z less than infinity. And so note that the book likes to write things in terms of z inverses. So likes to write this as x of z is equal to 1 over 1 minus z inverse. Now, to me, that's kind of ugly. I prefer to stick with polynomials and z. So that's the way I'm going to be doing it for you guys. All right, a couple more examples. So a more general example. Suppose that x of n is equal to, say, z0 to the n times u of n, where z0 is some given number. And z0 could be real, it could be complex, so we're allowing for complex valued signals here. Now, when I say more general, what do I mean by that? Well, notice that the unit step is actually of this form. You see what I mean? How do I make a unit step be of this form? Bryce? Yes, you set z0 equal to 1. So note x of n is just equal to the unit step when z0 is equal to 1. But anyway, so that's a more general example. z0 to the n u of n. What is the z transform of that? Plug it into the formula. So x of z is equal to the sum from n equals minus infinity to infinity, x of n, z to the minus n. And of course, this signal is in the universe of signals that vanish for n less than 0. This becomes the sum from n equals 0 to infinity of z0 to the n, z to the minus n. Okay. And now, remember what I said was, almost all the examples you see at this level are going to be things where you can figure out the formula for the z transform and the region of convergence all at once using geometric series ideas. How do we do that? We recast this as a geometric series. So this becomes sum of z0 over z to the n. Okay? That's a classic geometric series. Sum of n equals 0 to infinity, gamma to the n. Gamma here is equal to z0 over z. It converges to 1 over 1 minus gamma, which is z0 over z. And we can write this as z over z minus z0. And the series converges when the gamma thing is less than 1 in magnitude, so z0 over z less than 1, i.e. z0 less than magnitude of z less than infinity. So, bottom line for this example, x of n equals z0 to the n u of n has z transform, x of z is equal to z over z minus z0, and the region of convergence is going to be z0 less than magnitude of z, less than infinity. So that's the ROC. And I'm just writing that for completeness sake, showing you where it comes from. It comes from the fact that the series defining x of z doesn't necessarily converge. It only converges for certain z values. Those z values are going to be the z values in the region of convergence. And again, the book likes to write this x of z equals 1 over z, or 1 over, I can't even do it because I don't like it, 1 over 1 minus z inverse z0. Okay, I don't like using z inverses in these formulas. I much prefer the formulas in terms of z. All right? Now, you can go through a whole litany of examples of this kind. So we can generate a whole list of examples, so similar examples. And essentially what happens here is you get a big table. You make a big table that you're going to use later on for looking up things. Okay, so for a quote-unquote z-transform table, okay, now the table is going to start with a delta, and then it's going to have this example, and the general entry in the table is going to be this one, n choose m, z0 to the n minus m u of n. If that's my x of n, that's going to have z transform x of z equals z over z minus z0 to the m plus 1. And the region of convergence is going to be, again, z0 less than magnitude z less than infinity, and we're not going to worry about that too much. Okay, so this is for all integers m bigger than or equal to 1. And in fact, it works for m equals 0 if you go up to the previous example. All right, so we have this whole list of z transforms. All right, now it turns out that a signal and a z transform are in one-to-one correspondence. So x of n and x of z determine each other completely. So signals and their z transforms are in one-to-one correspondence, which of course justifies this double arrow notation that we've been using, just like we did for the DTFT. And in fact, we have a formula. There is a formula, an inversion formula that you can use to generate x of n from x of z. Thing is, we never use that formula, but I do want to note that it exists. So in fact, there's an inversion formula giving x of n from x of z, but as I said a moment ago, we never use it. We never, in this course, use it, and in real life, one rarely uses it. Instead, what we're going to do is, for the signals of interest to us, we're going to be able to decompose them into pieces that map to this table, this lookup table that I've generated up here. So instead, what we generally do is we decompose x of z into pieces that quote unquote map to the table above. Okay? Now, from the table, we put them together to figure out what the signal x of n is. So let me go through how we're going to do that. And first, what I have to tell you is the kind of z transforms that this works for. It doesn't work for all of them. Okay? So, turns out that the signals we care about have z transforms x of z that are what we call proper rational functions of z. Proper rational functions of z. Okay, so what is a proper rational function? What is a rational function? Okay. A rational function is the ratio of two polynomials. Like, polynomials are things like, z squared plus 5z minus 3, or z cubed plus 17. Those are polynomials. They're powers of z linearly combined. Okay. They're not things like e to the z or cosine of z or whatever. So polynomials in z, so they're going to be polynomials in z. P of z over q of z, I'm going to call them. So these are both polynomials. And that's what rational means. And proper means that the degree of the numerator polynomial p of z is at most equal to the degree of the denominator polynomial q of z. All right? Now, the properness part of this, I'm having trouble with one of my contact lenses. I hope you don't mind. I'm just grossing out if I stick my finger in my eye every now and then. But the proper part of this, the degree less than or equal to degree p less than or equal to degree q, that's going to correspond to x of n, the signal that corresponds with this x of z being in our universe, it turns out. It turns out that signals in our universe of signals that vanish for n less than 0, those are always going to have proper rational z transforms when they have z transforms at all. Okay? So, how do we figure out x of n from x of z when x of z is a proper rational function? That's the next order of business. So let's, how to get x of n from x of z in this case. All right. What we're going to do is first off, so first step, and the only reason we do this step is so that at the end of the line, the formula we get maps to our little table that we just put together. The first step, we divide by z, okay? We get x of z over z. And this is going to be what we call a strictly proper rational function of z. What does that mean? That means that the numerator degree is strictly less than the denominator degree. Not just less than or equal to, but strictly less than. Now, what's good about strictly proper rational functions is that you can expand them in partial fractions. So strictly proper rational implies you can expand in partial fractions. Now, you all know what partial fractions is, right? Like when you took calc, the first time you learned integral calculus, you had complicated integrands that were like ratios of polynomials, and you expanded them in partial fractions and evaluated the integrals that way. That was probably the first time you saw partial fractions, right? Am I right about that, Morgan? Well, then you must have had a really good secondary school because I didn't learn about partial. I don't think I learned about partial fractions in pre-calc. I think I learned about them in calculus, senior year of high school. But anyway, you've seen partial fractions before. You know how to do it. How do you do it? Use MATLAB or whatever, you know. But there's ways that I like to do it, and this is not going to work so well in my living room. You know, this isn't the appropriate venue for this. I mean, I really need a board, so I'm going to have to pretend I have a board here. So, for example, let me carry an example through this whole discussion. How about x of z is equal to z times z plus 2 divided by, say, z squared minus 3z plus 2, something like that. That's perfectly good rational function of z, proper rational function of z. In fact, it's strictly proper already. So what is x of z over z equal to here? X of z over z is equal to just plain z plus 2 over z squared minus 3z plus 2. All right, now to do partial fractions, we could have done it on x of z, but it's not going to help us in the end because we want to get things in the form of our table. So you'll see how that works out. So now, you expand this in partial fractions. How do you do partial fractions? Well, I have a way I like to do it. It's called partial fractions by Zen. And that's what I meant by this is not an appropriate venue to do partial fractions by Zen. I can only do partial fractions by Zen if I'm in front of a class and I have a blackboard that I can write on. So this is a first. I'm going to try to do partial fractions by Zen in my own home. Okay? So first what you do is you figure out what the roots of the denominator are. Right? What are they? They're 1 and 2. So this is the same as z plus 2 divided by z minus 1 times z minus 2. And then you do a partial fraction expansion. How do you do that? Well, first you just write over z minus 1 plus over z minus 2 with nothing in the numerators. Now, I'm going to bring this up to the camera so you can see what this looks like. And see if I can get this to come across right. See something over z minus 1 times something over z minus 2. Okay, how do you find the somethings? Well, you just kind of stare. You just kind of, you try to empty your mind and use Zen. So if there were a blackboard here, I would do this. I would stare at the blackboard and I would say, this is going to be minus 3 over z minus 1 plus 4 over z minus 2. Yeah, that's how I do it. Okay, partial fractions by Zen. It takes practice, but you'll learn over time. So that's a partial fraction expansion of x of z over z. Now multiply through by z to get x of z. X of z is equal to minus 3z over z minus 1 plus 4z over z minus 2, right? And now you use table lookup with the table that we formed earlier to figure out what x of n is. So finally, you get x of n by table lookup. And specifically, since z over z minus 1 has unit step as its signal, of which is the z transform, and z over z minus 2 has 2 to the n u of n as the signal, for which it's the z transform, we get x of n is equal to minus 3 u of n plus 4 times 2 to the n u of n. That's the answer. That's the x of n that goes with this x of z. Okay? So you do x of z over z in partial fractions, and that gives you x of z as a sum of terms that look like our table. All right, now, to be fair, it gets a little more complicated when you have repeated poles, repeated roots. I haven't even defined the word pole yet. When you have repeated roots in the denominator, it gets a little more complicated. So a bit more complicated when you have repeated roots of q of z, the denominator polynomial. But, you know, we're not going to worry about it because it's just a matter of computing stuff. It's no big deal. All right. So that's one example. That's one example of doing this. Let me just do one more example. This is just ever so slightly different. Okay, so a slightly different example that shows another wrinkle that might come up. X of z, and in this one I'm just going to have z plus 2 over z minus 1 times z minus 2. Before I had a z times z plus 2 in the numerator. Now I just have z plus 2. So what is x of z over z in this case? It's equal to z plus 2 divided by z times z minus 1, z minus 2. So, dividing by z introduces a new denominator root, namely 0. Okay? So, this partial fraction expansion is going to have 3 terms. And what are those terms going to be? Partial fractions by Zen. This is going to be a 1. Okay? It's going to be a minus 3 again. And this is going to be a 2. Check it out. I think it's right. I'm gonna assume it's right and move on. Okay, so all right, so anyway, that means x of z itself is equal to this. 1 minus 3z over z minus 1 plus 2z over z minus 2. All right, and what does that give us for x of n? From the table, x of n is going to be equal to, what goes with a 1? A delta. And again, we have minus 3u of n, and this time we have plus 2 times 2 to the n, u of n. That's my x of n, our x of n, that goes with this x of z. Okay? So that's an example. That's how you find the signal that goes with a given z transform x of z in a given situation. Okay? All right, now you know all about z transforms, as much as you need to know for this course. Back to systems. So let's back to our causal LTI systems governed by difference equations. What we're going to want to do is use the z transform to figure stuff out, like figure out the impulse response to the system, figure out the output of the system given a certain input signal. So how do we apply these z transforms? All right, well, the two keys to applying z transforms in this context are 2 operational rules for z transforms. So here are some 2 key operational rules for z transforms. And one of they're going to be, these are going to remind you, I think they're going to remind you of operational rules for DTFTs. First one is what's called the time delay rule, and I'm going to be very specific because we're dealing with signals in our universe, okay? So I want to make sure I only talk about time shifts that keep me in the universe, and those are time shifts to the right. My right, your left. Signal is 0 for n less than 0. If I shift it to the right, I still get a signal at 0 for n less than 0. So to stay in the universe, I can only talk about positive time shifts. So time delay rule says, if n0 is bigger than 0 and y of n is equal to x of n minus n0, then y of z is equal to z to the minus n0 x of z. And it turns out they're going to have the same region of convergence. I'm not even going to sweat writing that down. Okay? That's the time shift rule. Easy to prove, not going to waste class time on it. Okay? Guess what the other rule we want to use is. See if anybody can guess what the second rule is. Okay, Jack, non-CU error Jack, other Jack. Good job. To every transform, there is a convolution rule. So we have convolution rule. Okay, and that goes like this. If you have a signal h of n that has z transform h of z, and you have a signal x of n that has z transform x of z, then the convolution of those two guys, that's going to have z transform the product h of z times x of z. Very good. Okay. So those are two important rules. Two important rules. Now, I've used h and x as my letters here for good reason. What do h and x remind you of? H, that sounds like an impulse response. X sounds like an input. Okay? And sure enough, that's the kind of thing we're going to be talking about. So, what if I have an LTI system, okay, with an impulse response, say h of n, that has a z transform? Okay, so given a linear time-invariant system with impulse response h of n, we call the z transform of h of n h of z of h of n, if it exists, and remember, z transforms don't exist for all signals. What do we call that? What do we call that function h of z? Does anybody know? Critique. Yes, that's what I call it, and that's what we're going to call it in this class. The transfer function, that's why the book calls it the system function. I think that's an insipid thing to call it. It doesn't have any heft to it. To me, transfer function, that's what I was brought up on. You know, it's like whole grain bread or something. Anyway, so we call this the system's transfer function. Okay, so what does this mean in the context of the time shift and the convolution rule? Well, because when you have an LTI system, the output is the convolution of the impulse response of the system with the input signal. That means that the z transform of the output signal is going to be the product of the transfer function of the system with the z transform of the input signal. Okay, so by the convolution rule, this is worth starting a new page for. By the convolution rule, if you have an LTI system, with impulse response h of n and transfer function h of z, we have that the output y of n, which is h of n convolved with x of n, all right, so this is the output, and this is the input, that's x of n, has z transform, y of z is equal to the product of the z transform with the product of the transfer function h of z with the z transform of the input signal. And this is when x of z exists, when x of n has the z transform. All right? So that's good. And now, how do you figure out the transfer function of an LTI system? If you have the impulse response, you can just take a Z transform. Okay. But what if you don't have the impulse response? What if you have one of those systems like we were talking about last time, the causal FIR systems governed by a difference equation? We saw one easy example where it was simple to figure out the impulse response just by hand. But for harder systems, for bigger systems, that's harder. So here's a typical kind of application. You have a system, a causal IIR system. I think I was saying FIR a second if I meant IIR system, governed by this. Y of n is equal to the sum, a bunch of recursion terms, so sum from k equals 1 to cap n of ak y of n minus k, plus a sum of feed-through terms, so it's k equals 0 to n, bk x of n minus k. Okay? You have that kind of a system. And your goal is to figure out, so you want, well, what might you want to figure out? You might want to figure out the impulse response of the system, or you might want to figure out the output of the system corresponding to some given input signal. So, for example, h of n. You want h of n, the impulse response of the system. Or maybe you want y of n that arises from some z transformable input signal x of n, whatever. Okay. How do you go about doing that? Okay, how to proceed. All right, well, what I'm going to do is I'm going to take the z transform of both sides of the difference equation, and I'm going to apply the time delay rule while doing that. So first step is take the z transform of the difference equation and use the time delay rule. Okay, now what was the time delay rule? Now if we had a blackboard, the time delay rule would be like right over here. Time delay rule, but really it's on that piece of paper down there. So let's take the z transform of this difference equation. Z transform on the left-hand side is just y of z. Z transform on the right-hand side is going to be, well, the first sum is the sum of ak y of n minus k. Y of n minus k goes to z to the minus k y of z by the time delay rule. So I have ak z to the minus k y of z. Second sum, bk z to the minus k x of z by the time delay rule once again. Okay? What's the next step? Next step is you solve for y of z in terms of x of z. So you solve for y of z. So you move all the y of z involving terms to the left-hand side, and you get this. Y of z is equal to, I'll put big parentheses here, sum k equals 0 to n, bk, z to the minus k, divided by 1 minus sum from k equals 1 to n, ak, z to the minus k, all that, times x of z. All right? All right, so what's in the parentheses? What is that thing in the parentheses? What do we call that? What do we call that? Alex, no. Yes, this is the transfer function of the system because y of z equals h of z x of z. the way you get the z transform of the output is you multiply the z transform of the input by the transfer function. So this here is the system's transfer function. Okay? So let's write it out. H of z equals sum from k equals 1 to, or 0 to n, bk z to the minus k divided by 1 minus the sum from k equals 1 to n of ak z to the minus k. You can see that if I multiply through by z to the n, Newman denom, I get this. Sum from k equals 0 to n, bk z to the cap n minus k divided by z to the cap n plus minus the sum from k equals 1 to n, ak z to the n minus k. All right? What kind of a function of z is that in terms that we have discussed today? What kind of a function of z is that? Somebody. Nobody. All right. What kind of functions? How do I ask the question? How about this? It's a proper. Yes, thank you. Proper rational function of z. So note, h of z is a proper rational function of z. Okay? It's a ratio of polynomials in z, and the degree of the numerator is at most equal to the degree of the denominator. Some of the b's could be 0, so the numerator could have a lower degree than the denominator, but the denominator has unequivocal degree n, cap n. So anyway, it's a proper rational function. What does that mean? That means that we can find h of n by our partial fractions by Zen and table lookup. So partial fractions plus table. Okay, so that was one of the things we might have wanted to find, the impulse response of the system, right? What's another thing we might want to find? What if we have an input signal x of z? So moreover, if x of n is some input signal with a proper rational z transform, x of z, then y of z, being the product of h of z with x of z, is also going to be a proper rational function of z. And we know how to find signals from their z transforms when the z transform is partial or is proper rational. So thus can also find y of n by partial fractions plus table lookup. Okay, so z transforms, it turns out, give us a pretty powerful tool for analyzing these systems governed by difference equations. It's like if you came up to a whole plaza with this particular difference equation and n was any reasonable size, like 17, and all the a's were non-zero and all the b's were non-zero, and you asked me to find the impulse response of that system, I would not go and plug an impulse into the difference equation and figure it out term by term by term. I would not do it that way. I would do it this way. I would find the transfer function by this method here, find h of n by taking the inverse z transform of that. That's what I would do. And that's what I would suggest you do as well. Okay. So this is an example of how we apply z transforms to do algebraic manipulations and solve for various things to do with these systems. Okay? I want to mention, let me just check the time here. Okay, we got plenty of time left. I want to mention a special kind of system that we spent a lot of time on so far this semester, causal FIR systems. Those are a slightly different animal than these. Okay, so let's look, just for completeness, at the causal FIR systems. Now remember, these are a special case of systems governed by a difference equation, but the way the transfer function and everything comes out is very special. So I want you to see how that works. So causal FIR systems. Something's rocking here, so I have to fix this. Causal FIR systems. So in that case, you have something like this. Y of n is equal to sum from k equals 1. And I'm going to use cap m here instead of n, because that's what we use most of the time when we're talking about these FIR systems. So bk x of n minus k. All right? So when you've got a causal FIR system, we know how to figure out its impulse response. And we've done that a million times. What is its transfer function? Its transfer function is the z transform of the impulse response. So we could figure out the impulse response and then figure out its transfer function. Or we could do the same kind of manipulation on this difference equation that we did on the upper one to get the transfer function h of z. So let's do that just to figure out h of z, for practice using this technique. So let's figure out the system transfer function. I've got to fix this so it doesn't rattle. Transfer function h of z as we did above. Okay, so how do we do that? We take the z transform both sides. And we apply along the way this important time delay rule. Okay, so on the left-hand side we get y of z, that's a z transform of y of n. And on the right-hand side, by the time delay rule, we get the sum from k equals 1 to cap n of bk z to the minus k times x of z. And we can factor in x of z out of all those terms on the right, and we get k equals 0. This is 0 to n. I meant to say 0 before. So it's going to look weird when you see, you're going to see this transcript and you're going to see the 0 the whole time, and I'm saying 1, and you're thinking, why did he say 1 and fix 0? See, this is the disadvantage of not having a board, where I can go up and erase one little thing at a time. But anyway, I have k equals 0 to n, m, boy, cading here, bk z to the minus k. Okay? So, what's in the parentheses has to be h of z, because y of z equals h of z x of z. You can take that to the bank, that equation, okay? So what's in the parentheses has to be h of z. So thus, h of z, the system's transfer function, is sum from k equals 0 to m bk z to the minus k, okay? And we could also write that, if we don't want to write it in terms of powers of z inverse, and this is the one exception to my aversion to writing things in terms of z inverses. If we're talking about FIR systems, I like to leave the transfer function in z inverse form. But you can also write it this way. You can also write it sum from k equals 0 to m bk z to the m minus k divided by z to the n, if you want to put it in terms of powers of z. Okay, but like I said, this is the one situation where I generally leave the transfer function in terms of z inverse rather than z. Okay? So that's an example, a causal FIR system. That's what the transfer function looks like. Okay, so any questions so far? Any questions so far about the z transforms and how we're applying them for these causal FIR system or IR systems governed by difference equations? finding the x of n given the x of z. Okay. Sure? No questions? Okay. All right. Now I want to talk about an important concept for LTI systems. And I'm only going to be looking at this for causal LTI systems. And that's the concept of bounded input, bounded output stability. Very important concept. So I want to turn now to an important concept. And as it happens, this issue, the issue of whether a system is what's called bounded input, bounded output stable, which we'll define shortly, this issue never arises for FIR systems, as we'll see. But as soon as you get one of these recursion kind of things going, it arises. Now, we saw earlier that, you know, the discrete time integrator was not, well, no, let's keep it up. Okay, so now onto an important concept, bounded input, bounded output. And the standard abbreviation for this is BIBO, stability. Okay, now this is another one where some people, like remember I told you that if you said FIR instead of FIR, you would get laughed out of the lab. You know, that is true, okay? However, some people say BIBO stability. I don't. I say BIBO stability, okay? But I would say people are evenly divided about whether they say BIBO or BIBO. But one thing is, like, in one class where I taught about this concept one time, we actually had a student from Hong Kong whose name was Bibo, and she thought it was cool that there was a stability concept named after her. All right, so anyway, what is BIBO stability of a linear time invariant system? And we're going to talk, like I said, about this for causal systems only. So focus on causal systems only here, even though you can define it for non-causal systems. All right, so we say a causal LTI system is BIBO stable, okay, when the following is true. When every bounded input signal x of n. And this is an item that confuses people. So I'm going to try to be careful in describing what I mean by this. Every bounded input signal x of n gives rise to a well-defined output signal, y of n, that's also a bounded signal. Okay, so bounded inputs give rise to bounded outputs. That's the aphorism. Okay, bounded. Delicate concept for some people. What does bounded mean? This is the confusion. This is what people get confused about. We've learned about finite duration signals, right? Finite duration signals. They start at some point and they end at some point, and there's zero before and after those points, okay? They have a finite duration interval, bounded duration interval, you know, whatever, support interval, whatever we've been calling it, all right? What is a bounded signal? It's not, doesn't mean it's finite duration. It means it's bounded this way, okay? There's a roof and a floor above which and below which the values of the signal never go, okay? So this is duration, this is bounded. Bounded signals have a roof and a floor, okay? So for example, the unit step, that's a bounded signal because it never goes up above the roof of 1, right? Or below the floor of 0, okay? Right? Cosine of n omega 0 hat. That's a bounded signal because cosine is always between plus and minus 1. Roof of 1, floor of minus 1. What's a signal that's not bounded? Somebody give me an example. Yeah, n squared. X of n equals n squared. I was thinking e to the 3n. But you're right, you know, that Avisha's right, that n squared is just as good as e to the 3n. So e to the 3n, that's not a bounded signal. Why? Because there's no roof. It goes through every roof you could possibly build. You know, e to the 3n is climbing exponentially as n goes to infinity. So that's what bounded means. Signals, input signals that have a roof and a floor give rise to output signals that have a roof and a floor. But the cool thing is that the roof and the floor for the output need not be the same as the roof and the floor for the input. Okay. All right. So in terms of mathematics, you would say the following. You would say that so math-wise, if x of n has absolute value or magnitude less than or equal to R1 for all n, then there exists some R2, not necessarily equal to R1, such that y of n, its absolute value, is bounded from above by R2 for all n. Okay, so the roof and the floor don't have to be the same for y of n as they are for x of n. Now, how do you know whether a causal LTI system is BIBO stable? Here's the big basic fact. So here's fact. A causal system, I won't even bother throwing in the LTI, you know, we're always talking about LTI systems, with impulse response, H of n is BIBO stable if and only if H of n is what we call absolutely summable, or an L1 signal. So H of n is absolutely summable in the sense that the sum from n equals 0 to infinity, absolute value of H of n, converges. Okay, that's what absolutely summable means. And in particular, that means that H of n has got to go to 0 as n goes to infinity. You know, to make this series converge, that has to happen. And terminology-wise, we also say in this case, we say that H of n is what we call an L1 signal, or little L1 signal, if you will. That's what some people call it. Okay, that's standard terminology, and you'll see that, you know, L1, L2, all that kind of stuff comes up a lot. Okay, now why is it true? Why is it true that that this condition on H is equivalent to BIBO stability? Well, it's easy to prove one direction of this, that if this condition holds, then the system is BIBO stable. Okay, so we won't prove this, but just to see why this is a reasonable condition. Okay, so to see why this condition at least implies BIBO stability. Okay, consider what happens. Suppose it holds. So you've got a system whose impulse response is L1. It's absolutely summable. Let's drive the system with a bounded input signal. So with, say, x of n satisfying x of n absolute value is less than or equal to r for all n, r1 say. Okay, so this is a bounded input signal. It's got a floor and a ceiling, minus r, positive r1. Okay? What is y of n? Y of n is equal to h of n convolved with x of n, because that's what impulse responses do. They convolve with inputs to give you outputs. And that's equal to the sum over all k, h of k, x of n minus k. And because the system is causal, this is the sum from k equals 0 to infinity of h of k, x of n minus k. And this is by causality. Because remember, causality is the same as saying the impulse response is 0 for negative values of time. All right, so let's look at the absolute value of y of n. So for all n, we have that absolute value of y of n is equal to the absolute value of that sum. So absolute value of sum from k equals 0 to infinity, h of k, x of n minus k, which is less than or equal to the sum of the absolute values. That's one of those things you learned when you were a kid, or if you were in Morgan Quality School, you learned in middle school or whatever. So absolute value of x of n minus k. But all these guys, these x's by assumption, these are all less than or equal to R1, right? Because x has a ceiling and a floor. So this is less than or equal to sum from k equals 0 to infinity h of k times R1. This parentheses thing is finite by assumption. So that means that y is also bounded. So y of n, absolute value, is less than or equal to R2, which is equal to that whole thing. Okay? Bounded input signal gives rise to a bounded output signal if the impulse response happens to be absolutely summable, happens to be an L1 signal. Okay. All right. Now, how does BI-BO stability manifest itself in the transfer function? Okay, that's the next question. Okay. So this is BI-BO stability. This is the complete time domain characterization of BI-BO stability. Now what we want to do is we want to look and see what properties of the transfer function correspond to BI-BO stability. So what about BI-BO stability in terms of the transfer function? Let's say in terms of a system's transfer function. Okay, so like what property of a transfer function corresponds with BI-BO stability? Well, it turns out that there is a nice general way of talking about this, but for our purposes, it's a lot more interesting to look at the specific case where we're talking about a system that has a proper rational transfer function. Okay? So this is cleanest when we're talking about, so we're dealing with a causal system with a proper rational transfer function. Okay? Now, what is the condition here? Suppose your transfer function is this. So say you have h of z is equal to p of z over q of z. All right? The roots of the numerator polynomial are called zeros of the transfer function. And I'm going to spell zeros without the E, so zeros, sounds like a Greek surname. The roots of P of Z are the zeros of the transfer function. All right, and I'm assuming you've expressed this in lowest terms, so there's no cancellations between P of Z and Q of Z. all the common factors are gone. The roots of q of z, anyone know what they're called? Yeah. So, Sam, where did you hear that before? Yeah, circuits. You probably talked about the poles, the transfer function, but then you were talking about Laplace transforms. But anyway, these are the poles of h of z. All right. So the roots of h of z, the roots of q of z are the poles of h of z. It turns out, okay, here's a fact. Fact is that a system with a proper rational transfer function is BIBO stable if and only if all of its poles, all the poles of h of z lie inside the open unit disk magnitude of z less than 1. Okay? So that means that there can't be any poles that have magnitude 1 that are on the unit circle. There can't be any poles outside of the unit circle. There can only be poles inside and not on the unit circle in the open unit disk magnitude of z less than 1. Now, how do you see this? Why is this the case? Why is this the case? I'm not going to go through the detailed proof, but here's the basic idea. Basic idea. The basic idea is that h of n is going to be a combo of terms like, so if h of z will have some poles. The impulse response by our partial fraction table lookup, so using partial fractions plus table, h of n is a linear combo of terms like z, or no, not z, because we're talking about z over z minus z0. That's the partial fractions of terms like z0 to the n u of n. Where z0 is a pole of h of z. So, like for example, say, e.g. if h of z is equal to, say, 3 over z minus 1 minus 4 over z minus 2, then h of n is equal to 3 u of n minus 4 times 2 to the n u of n. So it's a linear combo of terms 1 to the n u of n and 2 to the n u of n when h of n has poles 1 and 2. Okay. Now, for the system to be BIBO stable, all the terms in h of n have to go to 0 as n goes to infinity. So for system to be BIBO stable, for BIBO stability, all the terms in h of n certainly need to go to 0 as n goes to infinity. Because otherwise, h of n would not be absolutely summable. Okay? And that's what it has to be for the system to be BIBO stable. Thus, we need magnitude of z0 less than 1. Because otherwise, this z0 to the n u of n is either going to explode or it's going to oscillatorily grow in magnitude. Or stay flat, if z0 has magnitude 1. So thus we need z0 less than 1 for BIBO stability. And since z0 was an arbitrary pole of h of z, And since this has to be true for all the poles of h of z, because all of them are going to appear in some term of the impulse response, we need all the poles to be in magnitude of z less than 1 for the system to be BRBO stable. Okay? And the converse is also true. You know, the point that I'm just trying to give you the basic idea of why BIBO stability in terms of the transfer function has such a simple characterization in terms of pole locations, at least when the transfer function is a proper rational function of z. Okay? So that's a very important idea. All right? Those are the generalities about BIBO stability. Now, what I want to do is look at a bunch of the systems, the kinds of systems we've been looking at over the course of the semester, just to see which ones are BIBO stable and which ones aren't. Okay? And in each case, we can sometimes reason directly from the system description to see right away that it's BIBO stable without figuring out anything more. But in other cases, well, you'll see. Okay. So let's look at some sort of general example systems. Okay, some general and specific example systems. Let's just say specific example systems. Specific example systems for BIBO stability. So we're going to check for BIBO stability. And this will wrap it up for today with this. Okay, so what were our first examples? Let me just make sure I time this right. You don't know how much I rely on having like a clock in the back of the room telling me about how much time is left, because then I can, anyway, I don't have such a clock here. So, all right, so how about, remember we talked about systems first time. What were the first two systems we talked about? The zero system and the identity system. Are they BIBO stable? Remember, what does BIBO stability mean? It means if we put a bounded input signal at this system, the output signal that comes out is also bounded. Is that the case for the zero system? Yes, obviously, because no matter what input we put in the system, the output is the zero signal, and that is trivially bounded. What about the identity system? If I put in a bounded x, remember bounded is about the roof and the floor, it's not about this. If I put a bounded x into the system, what comes out? It's the identity system, so x comes out. So the same bounded x comes out. Bounded input, bounded output. So the zero and identity systems are BIBO stable. Okay? What about the pure N1 shift system? And here, let's assume that N1 is non-negative, so we're talking about a causal pure N1 shift. What about that system? If I take an input signal and I shift it, does that change the fact that it's bounded? No, it stays under the same roof and above the same floor. Bounded input, shift, you get a bounded output. Okay. What about the m-fold averager, say a causal averager? So y of n is equal to the sum 1 over m times the sum from, say, k equals 0 to m minus 1, x of n minus k. That was one of our primordial example systems. What about that one? Is that BIBO stable? If I have a bounded input signal, remember, bounded is about up and down. It's the top and the bottom of the values. It's not the time duration. So if I put in a bounded input signal, and the output at any given time is the value, the average value of those numbers in a sliding window of length m, is that always going to be a bounded signal? Or are all those averages going to be bounded from above by something? From below by something? Yeah, because if I have a bunch of points, all of which are under the same roof and above the same floor, and I take the average value of those points, the average value is still going to be below the same roof and above the same floor. Okay? So yes, and let me just write the aphorism for this. You average a bunch of values. Above same floor and under same roof, you get another value in there. So the same floor and roof that work for the input signal x of n work for the output signal y of n in this case. Okay, final example. Final example, discrete time integrator. Is that VIBO stable? If I put a bounded input signal into that, do I get a bounded output signal? What was the discrete time integrator again? It was this. It was y of n is equal to the sum from k equals 0 to infinity, x of n minus k. It's the value at time n of y is the sum of all the previous values of the input signal x. Is that VIBO stable? Okay, why don't I leave you with that question, and we'll pick this up in the last lecture. This is the second to last lecture, and for now, I will put the pen down and I'll walk up to the piano. You're sitting. This is sitting on top of the piano, by the way. You might want to know. And this thing is like a makeshift lectern made from a keyboard stand. Okay, this keyboard stand over here, and this top thing is like a little tray that we used when I was a little kid when I had my tonsils out, so you can bring me food in bed. How about that? I still have this thing kicking around. So anyway, I will put the pen down and I'll say that I miss you guys and I look forward to seeing you sooner than later. And for now, I hope you're doing okay wherever you are, and I'll talk to you soon.